Hello everyone, in this video I'm going to be discussing vectors and some particular uses of them and how they're applied in physics. So first off, what is a vector? A vector is an object composed of these two things. Let me underline vector. Direction and magnitude. Now, direction really is the angle of the vector and the magnitude really is the length of the vector. So in other words, if you have any two vectors with the same angle and same length, then they're equivalent, they're the same vector. Now, a visualization of a vector, we typically think of this arrow scenario, where we have the tail of the arrow and the head of the arrow. That'll become a little more important later on. And you'll notice that they have different angles. In this case, the angle from the horizontal is given by this. Here, the angle from the horizontal would be negative in this case, or if you want to think of it as positive, it would be this obtuse angle. It's actually bigger than 180 in fact. Here the angle would be 0 degrees because it'd be horizontal angle, and their length would just be the length of the arrow, so the magnitude is the length of the arrow. The other thing I want to discuss here, of course, is the notation for vectors, and it's kind of a strange notation. You can kind of see it here. It's a arrow hat on top of the letter that we're labeling the vector as. So for instance, if this vector is labeled as v, v itself would represent a number. It's a variable for actually a number. But if you have the arrow on top, that signifies the actual geometric object, which is the whole vector itself. Okay. Now, different books use different notations. I quite like the one our book uses actually. It's basically just this. So the length of the vector, the magnitude of the vector is just v without the arrow on top. So if you see without the arrow hat, and then that stands for the magnitude only. Now I'm just going to show you because other books may use different things and I don't want you to get confused if you see something somewhere else. So typically the magnitude notation is a double absolute value. So the double absolute value or magnitude of a vector, v with the arrow on top, is just, in our case, v without the hat on top. So that's the notation for magnitude. So now we'll get into components of a vector. So again, there's an angle, so we'll call that angle theta. And here we have these components. There's the x component and the y component. So horizontal and vertical components of this vector. And there are a few things that we'll kind of note that are of in particular interest. First off, notice we have indeed a right triangle here. So we can apply some right angle trigonometry. And we'll find out a few things. So first off, if you take sine of the angle, it's going to be, well, the length v. So remember, the length is the magnitude of the vector, which is vy without the hat. Similarly, the length of this vector v is v without the hat, and the length of this vector here is vx, but without the hat. So again, without the hat, it stands for the length of the arrow itself. Great. So now what? Well, now again, if we take sine of the angle, we'll get opposite over hypotenuse. And if we multiply both sides by v, we'll get vy is equal to v times sine of theta. Similarly, if we take cosine of both sides, or cosine of this angle, we get vx over v, multiplying by v will give us vx is equal to v times cosine of the angle. Great. And then, of course, what happens if we take tangent? If we take tangent, it's just vy over vx, actually. But the benefit here is that we can actually find the angle by taking tangent inverse of that ratio, vy over vx. So this gives us a few different things. It basically gives us a way to find components of a vector, using these two, to find the angle of the vector given those components, if you don't know the angle. So if you do know the angle, you can find the components. But if you don't know the angle, but you know the components, you can find the angle. Okay, good. Now, there's something very particular here, and it's a little hard to say in words, but remember that when I introduced tangent inverse, sine inverse, and cosine inverse as well, in the last video, I said that the angle has to be in between 0 and 90. Now, in reality, in your calculator, the possible value of the output of tangent inverse can be in between negative 90 degrees and positive 90 degrees. So that's basically in what is called the fourth and first quadrant of the unit circle. But again, I don't want to get into too much trigonometry details there, but I'll say this. I'll say that if you take the absolute value of this, that'll give you what is called theta bar. So theta bar isn't necessarily theta, but it is what is called the reference angle. Now what the reference angle is, spell it correctly here, I'll use that symbol for angle. So what the reference angle is basically the angle to the x-axis, to the horizontal. So here, this would be the reference angle. I said it was negative, but if you take the absolute value, that's the reference angle itself. And you can find the full angle by doing 360 minus that angle in this case. So there are kind of different scenarios that I can kind of show you here. So I'm not trying to draw an XY plane or anything. This is just me kind of separating the different scenarios. So our arrows are either pointing in those different directions. Now in this case, theta is equal to theta bar. In this case, theta bar would be this. So that means theta, if you imagine the angle starting from the positive x-axis, would actually be 180 minus theta. So this implies that theta is equal to 180 degrees minus theta. And that I think is a little bit easy to compute once you actually see it in its own setting. When you see it with all of this, it looks a little overwhelming. But remember that we're always starting from the positive x-axis for our theta value. Basically, we want the arrow to be shaped like this. So to be quite honest, for most of our purposes, we'll be seeing an angle that's from 0 to 90 anyways. But I'm just trying to show you, if you have a vector in two-dimensional space, it could be facing in reality in any of these situations. So just to kind of speed up the process and show you, this is theta bar, then theta would be theta plus 180 degrees actually. You think about that. Here, this would be the reference angle theta bar. So here the angle would be 360 degrees minus theta bar. And again, you can think about these situations if you want, but mostly we'll be taking a look at the scenario where we only get a positive value. But if you get a negative value, it doesn't necessarily mean it's down here. It's just the way tangent inverse works. So in reality, to find the other ones, you would take the absolute value of this and see which case it is. But that's getting a little too technical. But just wanted to show you the detail of that. The last thing before we move on is how can you find the magnitude of a vector given its components? That's actually quite easy. It's just Pythagorean theorem. So notice that v squared is equal to vx squared plus vy squared. So if we square root both sides, we get that for v. And notice when we square root, we get a plus or minus, but since we take v to be the positive length of the vector, its magnitude, then we don't need to care about the plus or minus, just worry about the positive root only. All right, so now I think I've kind of given us some motivation to move on. Now we'll take a look at an example, and beyond this, I'm going to show you how to add two vectors, and then we'll actually subtract two vectors, and we'll see what that's all about. All right, so here for this example, we're given that Superman flies at a downward angle of 30 degrees from a window, and we want to find its component vectors if its displacement is, well, it's just a funny way of saying 100 meters. So displacement, by the way, just means distance that he has moved since. So total distance moved. So let's just say that this is the window that he's flying from. Let's say the window is actually here, so we have a little bit of distance, something like that. And let's just say this is kind of like our horizontal. That's good enough. And he's flying downward like this. So he's somewhere over here. I'm not going to draw the picture super accurately, but yeah, something like that. You get the idea. That's his arm. That's fine. So we know that the displacement of his distance really is d equals, I'll just write 100 meters. So what we have here is a vector. We also know the angle here is 30 degrees downward. So really what I said earlier, this corresponds to a negative angle. But for right now, let's just treat it like this. We'll get a right triangle going, and then hopefully we can find the component vectors. And maybe you can just kind of see it right now. Really the component vectors are this for the vertical. Let's call that Vy. and then this for the horizontal. Let's of course call that Vx, where our vector here is V. So all we know is this is V, so V is equal to D without the, just using our notation. In fact, using this notation, it kind of wants me to write D with a hat, and then this would be dy and dx, but I'm just going to use V, but that's okay. So let's see, so I'll kind of use V even though they ask us to use D. But again, the notation doesn't really matter, I just want to be a little consistent, that's all. So let's see, we want to find the component vectors, we want to find Vx and Vy. Now, Vx is, well, we know the magnitude of Vx at least. The magnitude of Vx will be, it's going to be V times cosine of 30 degrees. So we could just use our calculator here, but notice V is 100. So this is really 100 cosine of 30 degrees. Again, make sure your calculator is in degrees in order to actually compute this, and let's see what we get. All right, so my calculator gave me about 86.6, so approximately 86.6. And this is, of course, in meters because the displacement was given to be 100 meters. So I'll underline that. And then for Vy, this is going to be 100 sine of 30 degrees, which I've also calculated, which gives me about 50 meters. Now, there's a few things to keep in mind. So notice I said that what we spoke about previously, this was a negative 30 degrees. So if we took this to be negative 30 degrees and plugged it into our calculator, it would actually make a lot of sense because cosine of negative 30 multiplied by 100 will still give us this answer, but sine of negative 30 multiplied by 100 will give us negative 50, which makes sense because notice for the vertical, we're going down, whereas with the horizontal, we're going in the positive direction. So even though we only found the magnitudes of these vectors, not the actual vectors themselves, we know their direction. We know this one has an angle of 0 degrees, and we know this one has an angle of, I guess, 270 degrees. Kind of think of this being a full 360 rotation. 180 would be over here, and then this would be 90 more, so that's 270. But a kind of more mature way of thinking of it is that really this would have a positive magnitude where this would have a negative magnitude because it's going down. So if you want to treat this as negative, I think that'd be probably a better way of seeing it. I know I'm not being very specific as far as how I want the answer here, but right now we're just using this as motivation to get to something greater that we'll kind of see this way of seeing it will make a lot more sense. Okay, so now that I'm done with this example, I want to talk about addition and subtraction of vectors. Now, in order to add two vectors, there's a way to do it visually, and from that we'll actually see the way you would do it without the visualization. But the visualization is really where things kind of start to get nice. So notice that what I said at the very, very beginning when we first introduced vectors, I said if two vectors have the same direction and the same magnitude, then they're the same vector. So what that really means is we are actually allowed to move vectors around in two-dimensional space, so long as we don't mess with their length or their angle. If their angle and their magnitude are the same, the direction and magnitude are the same, then we have kind of infinitely many copies of the same vector if you think about it. So its location in two-dimensional space doesn't really make a difference. So with that being said, we can move one of these so that its tail touches the head of the other one. So what I really want is I want that to happen. So I'm going to imagine moving this over here, keeping the same angle and the same magnitude. So imagine this is still V, like this. And for you, if I connect it like this, again, I'm trying to make it so that it has the same length, maybe it's a little shorter, it's fine, and the same angle. So it looks somewhat accurate. Now, how you add two vectors geometrically or visually like this is you just connect them head to tail and then go from the tail end of the entire connection to the head of the entire connection. And what you end up with is a new vector, which is usually referred to as the resultant vector. And this red vector that I've written for us is really just the vector v plus u. So adding two vectors gives you a new vector, And it's pretty interesting because, as it turns out, the magnitudes are not necessarily the same, but they're kind of, well, they're not necessarily the addition of these. So the magnitude of this resultant vector is not necessarily the magnitude of these added together. You'd actually have to find their component to do that, to actually find out what that is. But at least we can add component-wise. So let me just say that u plus v is not equal to, sounds kind of funny when you write it like this, but it's not equal to, just to kind of use the other notation, the magnitude of this vector. So you know what, maybe instead of using the notation, let's do this. Let's call this new vector r for resultant. So even though u and v as vectors add to the vector r, it's not necessarily true that the lengths of v and u will add to the length of r. And that should make a lot of sense, because if you were to add these two lengths, you'll get this kind of straight line length. And if this is tilted down a bit, this is clearly going to be shorter. So the red length here will clearly be shorter than the sum of these two lengths. Right. But what we can say, though, is the following. We can say that the x components added together is the x component of the resultant vector. And similarly, the y components add together to form the y component. Now, I know this sounds a little confusing, but again, we're going to keep that in mind right now. Their component vectors add straight up, but the magnitudes do not. So now let's take a look at an example, and then I think that'll be the end of this video. But before we move on, let me say that we're really only handling addition here. I don't think I'm actually going to do an example on subtraction, but I will say this. If you want to subtract visually, like here I showed you how to add visually. If you want to subtract visually, depends what you're subtracting from. So v minus u or u minus v. But let's say you're doing v minus u. If you wanted to do v minus u, then that means the resultant vector will be v. So imagine this is v here. And then u will be one of the components that would add to v. And the other component that would add to make that, so let me draw that in red here, would be the subtraction. So this vector here would be the vector v minus u, because we're subtracting u from v in this case. And if you wanted to do the other way around, u minus v, then u would be the one that is adding to. So you get kind of a different image. And I'll let you kind of think of that on your own. But I really only want to do one example now. And again, I'm going to do an example on addition. So let's take a look at that right now. Right, so here I've drawn an image. I've attempted to draw the image anyways of this example I want to do. I was going to write out what it actually says, but it's a little lengthy in words. So I figured I'd just draw the picture and explain what's going on. So you have these two guys pulling this wild horse from these two ropes. And they're using different forces, which we're going to take to be the magnitude of these vectors at different angles. So we have direction and magnitudes for these vectors. They represent forces that are measured in newtons. So this capital N stands for newtons, which is actually a unit of force, and we'll see in a later chapter. So there's a lot actually happening here that goes a little beyond what we want to see in this section. But right now, all I want to do is take a look at these vectors and see how we can add these vectors. So really what I'm asking is that what direction is the horse going in? So notice I made this arrow look longer because the magnitude here is more than the other magnitude. So is he going to end up going this way? Is the horse going to end up going that way? Is there any way we can actually find out? So instead of drawing the actual arrow, what I want to do first is I'm just going to do this. So we have these two vectors. So let's just kind of think of this visually. We have this one vector here and this one vector here. We know their magnitudes, we know their angles. And we know somewhat how to find the sum of these two vectors. So the resultant vector will actually be where the horse will end up going overall if they stay consistent with these angles and with these forces. So they've applied the same force and they do not move at all, they don't move their angle, and the horse will have what we're about to find out as its overall trajectory, you can say. So think of it like this. Remember, to add vectors, we want to move one so that the tail end touches the arrowhead of the other one, the head end of the other one. So I'm going to move this vector over here, like this. So I'm going to draw that like kind of dashed. But this is the same vector here, so I'm floating it over. So I guess we can label these, well, they're kind of labeled for us, F1 and F2. So here this is vector F1, here this is vector F2, and I floated F1 over so that it's lined up just like we like, and now we can actually find the resultant vector. And it looks like the resultant vector will actually lean more toward the guy that's pulling with more force. So we'll call this R being a resultant vector, which is the sum of F1 and F2 as vectors. So the horse is going to be moving in this direction, basically. Now we can actually find the angle, and moreover, we can find the resulting force that both of these two are applying. Now, something to note that's actually pretty interesting is that if they were at the same angle, if they're both pulling in front of the horse, then their forces actually add up precisely. And the reason why that happens is because if they're both at the same angle, if they're both right in front of him, right in front of the horse that is, then notice they're both going to be purely vertical vectors. And what did I say about adding vectors? They're components add. But if a vector is purely vertical, then there is no x component, and it itself actually is its own vertical component. So if you add itself with the other vector, so this vector with that vector, if they're both vertical, then yeah, you can add them straight up. But in this case, a little more specific. So sorry for the digression, but let's see if we can figure this out. So what we can do is we can remember that, well, F1x without the hat, so the magnitude, plus F2x is equal to Rx. So their x components add up and their y components add up. So F1y plus F2y is equal to Ry. And we can actually find the components for each of these. So let's see if we can do that over here. We want to find their magnitudes only. So F1x, remember like this, F1x is equal to F1 times cosine of the angle of F1, which is 60 degrees. So I'll figure out what that is shortly. Also notice F1 is 120, so I can write 120 cosine of 60. So we'll find out what that is in a second. That's going to be in newtons. And then we can find, I guess, F2x. That's going to be the magnitude of F2, which is 80, times cosine of the angle of F2, which is 75 degrees. We'll find out what that is in a second. And then, of course, we can do the same thing for the y components of F1 and F2. So notice for the y components, we'll be doing the same calculation, only with sine instead of cosine. So this will be 120 sine of 60. Maybe a little bit of space for approximation. And then for F2y, this is going to be 80 sine of 75. And these are also going to be both in newtons. Great. So once we have these, we can add these results together to get the x and the y components for our resultant vector finally. So let's use our calculator and see what we get here. Alright, so this is what I ended up getting after using my calculator for F1x, F2x, F1y, and F2y. So now we can finally add these to find out what Rx and Ry are. So if I add the x's to find out what Rx is, we will get, let's see, so we're going to add these two together, we'll get 80.7, and that's in newtons. And for Ry, for the y component of this resultant vector, adding the y's, we get, let's see, that's going to be, we got 103.9 plus 77.3, so that's going to be in total 181.2, I think. Let me just kind of double check this real quick. Yeah, good. All right, so we have these two component vectors, and we can kind of try to figure out what that entails here. But as far as the actual magnitude of this vector, well, we know magnitude of a vector is the square root of the sum of the squares of its components from Pythagorean theorem. Great. So we can actually square these, add them together in square root, and let's see what we get. And so approximating to the 10th decimal place, so one decimal place, gives us 198.4 4 newtons. And yeah, so that's going to be the overall resulting force here, which makes sense if you think about it, because like I said, if they were both in line like this across the vertical axis, you would just straight up add their forces, and we'd get 80 plus 120 is 200. This is a little less than that because they're not quite lined up, so their overall force will be a little less than them being lined up. But the angle will be off as well. Okay, good. So now can we find the actual angle? Well, we can, but let's think for a second here what's going on. So see, I don't think this is going to be too difficult to see, but let's see. So remember we discussed that the angle is tangent inverse of the y component divided by the x component. So really all we need to do is divide 181.2 by 80.7 and take tangent inverse of that. So notice Ry is just 181.2 newtons. Rx is 80.7 newtons. I'm not writing the unit because unit will cancel here in the division. And now let's see what we get with our calculator. I actually did it already. So I got 66 degrees about, if you round. But at least we know how to find the angle. It's just tangent inverse of that. But you have to, again, be a little careful. You have to be certain what quadrant you're in. But we know this is in the first quadrant here. Otherwise, if we get a negative value, it doesn't mean it's down here. It could mean that it's over here. So again, if you take the absolute value, you get the reference angle in that quadrant. So we know how to handle it now based on that, hopefully. But in any event, we're done in the sense that we have found the vector. So again, I didn't write the direction of the example here, but I want to find the overall resulting vector of the trajectory of the horse, basically. And what is a vector? It is an object composed of magnitude and direction. We found the magnitude and direction, so this is actually the vector. So we can say the vector will have magnitude this. So let's box this. So this is the magnitude of the vector, and this is the angle of the vector, the direction of the vector. So if you want, I'll just label them. This is the magnitude, and this is the direction. So with magnitude and direction, we have uniquely found our vector. Great. So it's a good place to stop this video and our discussion on vectors. And we'll see more vectors. We'll see more vectors coming back to bite us a little bit, just a little bit, once we get into two-dimensional direction and two-dimensional motion, actually. But we'll see that in a few videos. Anyways, I'll see you in the next videos. Thanks for watching. Hope you enjoyed. See you then.